Hi again everyone, Chris Tisdell here again. In this presentation, I'm going to continue my series of videos on vectors. And in recent videos, we've been looking at lines and parametric vector forms of lines, Cartesian forms of lines, and sort of switching between the two. In this presentation, I'm going to give a simple example where you're asked to determine various equations describing a line when you're given 2 points that lie on the line. So let me share my screen with you and we'll get started. Okay, so here is the example we're going to discuss. Consider the points A and B. Determine a parametric vector form of the line L that passes through A and B, and also determine the Cartesian form of L. Okay, so let me just draw a little picture here to sort of give you a sense of what's going on. So we've got a line L, and we know that 2 points on the line. Okay, and let's just draw the origin in down here. Now, if I want to get to any point on the line, I know, so say that's the point big X. I want to form the position vector O big X. Okay, well, I know by the triangle rule I can just go out to this known point A and I can form a vector from the point A to the point B. So I go out from here to here, then here to here, and what I can do is stretch this vector AB to get up or down to the point of interest or any point on that line L. Okay, so the parametric vector form of L is the following. Okay, where A is just a position vector, or OA, of the point A. V is a vector that's parallel to L. In this case, V is going to be, or can be chosen to be, the vector AB. So all I really need to do to get the parametric vector form is compute the vector from A to B, the vector AB, and write down the position vector of A. Okay, so let's write down the position vector first. So basically just taking this and writing it as a column vector. And in this case, the vector V that's parallel to the line is the vector AB, because if A and B lie on the line, then definitely the vector from A to B is parallel to the line as well, right? Okay, so we know the vector between 2 points is just the difference of 2 position vectors. Okay, so let's take the coordinates of B, write them as a column, and take away the position vector of A. Okay, so that's going to give me 3 minus, so just work in a component-wise fashion, 3 minus 2, 2 minus 2, 1 minus 5. Okay, so I've got this part, I've got this part. Let's put them together. Hence a parametric vector form for the line L is, okay, now by this, I guess I can write it like this. By this boldface X here, I mean the column vector x, y, z. Okay, where x, y, z is the coordinate on the point on anywhere on the line. Okay, so A is this, and the v was just the vector AB. All right, so we're pretty happy about that. We've got our parametric vector form for L. So that's the first part of the question. So let's move on to the second part of the question. Determine the Cartesian form of L. Okay, well, I've talked about this in previous videos, but the Cartesian form in R cubed, or three-dimensional space, is just the following. Well, a line L that's parallel to a vector V with the coordinates V1, V2, V3, and passes through the point A with points A1, A2, A3, is just the following. Usually you cover that up and you just write it like this. Okay, all right, so we have a vector that's parallel. We have a point on the line, so we can actually use that bit of information to get the solution to part 2. So the Cartesian form of L is the following. Let me just write that out. It's the following. So A1 would be 1, A2 would be 2, A3 would be 5, V1 would be 2, V2 would be 0. So there's a problem here, okay? V3 would be -4. So what do? We can't divide by 0. So what do? We have to do still describe it in some way. So let me show you what we do. Okay, so it's x minus 1 over 2. Now we're going to leave that for a minute. Z minus 5 over -4. And what do we do here? Well, we basically forget these and write y equals A2. So A2 would be 2. Okay, so that's a little bit trickier because one of the v's, if you like, or the vi's, was 0. So that's how we would describe it in Cartesian form. Okay. Okay, so we started with 2 points on the line. We produced a vector from one point to the other point, and we also found the position vector of one of the points on the line. We used that to form the parametric vector form for the line, and then from that it was pretty easy, or from that and that it was easy to get the Cartesian form of the line. Okay, so that's the end of the example. Hope you enjoyed it. In forthcoming videos, I'll do some more examples on lines and how vectors and lines kind of go together and with the relationships between the two. So I hope you can join me for those presentations. If you have any suggestions, any feedback, just put it in the comment section below. Thanks for watching.